Okay, before we jump into some techniques for solving these differential equations, so remember, solving a differential equation amounts to finding the function that, when plugged in, when you take its derivatives, when plugged into this equation, makes the thing true. So the solution to a differential equation is a function. Before we jump into techniques for how to solve this algebraically or using our calculus techniques, I want to talk a little bit about these things called slope fields, which are not only a way of using a picture to estimate what's going on, but also a good way of really understanding what the moving parts are for a differential equation like this. All right, so we're going to start off with one of the simplest differential equations we can come up with. The derivative of the function at any given point is the value of the function at that point. So put another way, the derivative is equal to the value of the function. All right, and so what does this tell us about the function? What do functions that meet this criteria look like? Well, one thing we can do is look at the slope field. So we can see down here what a computer-generated slope field looks like. I'm going to do this one, at least the start of it, by hand. The idea is at every point in this plane, wherever we are, I want to be able to write down what the slope of the function should be at that point. So if the function goes through that point, we want to know what its slope is. So the idea is, well, if our function depends on what the y value is, if our y value is something like 1, then our slope should be 1. And we're going to record that by drawing a little line segment that has a slope of 1. And this equation doesn't care what the x value is. So all of the, whenever our y value is 1, our slope is going to be 1. And so we can draw a whole bunch of these, but the idea is that as we increase, as we go upwards, our slopes are going to increase. So we've got at 2, the slope is 2, at 3, the slope is 3, etc. And this starts getting harder and harder to draw, but the general idea is that the slope is only a function of what the y value is. As we get closer to 0, these slopes are going to get flatter and flatter. And I'm already regretting making this as big as I did. But the general idea is that, yeah, the slope is whatever the y value is. Whenever we get negative, so at -1, the slope should be -1. So if we extend this picture, we get this. And just like before, we're going to have a more gentle slope when the absolute value is smaller, and then a steeper slope when the absolute value is bigger. And we get a picture that looks like this. Okay. So one advantage of a slope field is that you can imagine starting at any given point. So if we happen to be right here, let me use another color. If we happen to be right here, we can sort of trace out what that function should follow. So we're going to go with the flow, and it's going to look something like this. And we can intuitively figure out what that shape is just by looking at what the slope field does. Another function might start over here, which is going to look more like this. So just like with our deer example that we did last video, where there were infinitely many solutions, and we can figure out what those solutions look like. With this one, we're figuring out what the shape of these functions look like just by looking at the slope field. Okay, I want to do another couple of these. So this is the slope field for the differential equation y prime is y plus x. And for now, I'm going to keep writing it in multiple ways. This is the same thing as dy dx is y plus x, which is the same thing as f prime of x is f of x plus x. These are all different ways of writing the exact same thing. We're most often going to use this middle one. But anyway, the idea is whatever, so with this one, it doesn't, the slope not only depends on the y position, but also the x position. If we look at the point 1, 1, it's not quite drawn here, but that should have a slope of 2. If we looked at a point -1, 1, that's about here. That's going to have a slope of 0. And you could test more points and sort of get an idea that, hey, this slope field is, the way to come up with this is just say, all right, for every point that we're drawing, figure out what y plus x is and draw a little line segment of that slope. So again, to get a sense of what the functions look like that meet this condition, we can pick any starting point and go with the flow. So I picked the point here, which basically says, oh, that's really bad. Basically says to follow this line. Looks something like that. A point more over here. These also don't change much. It looks like it's going to tail off this way a little bit. Another function that started, let's do the one that's right here, is going to go like that. Please ignore the wavy bits. Anyway, so just by starting with the slope field, we can get a sense of what all the functions that meet the condition should look like. Okay, and then the last one here, I lost the start of it. This one, I believe, is the function, or the slope field for the differential equation dy dx is y minus 2 times y plus 1. If we plugged in something in the middle, I believe there's a negative here then. Anyway, and with this example, we get slopes functions that look something like this, as well as other functions that look like this. Anyway, again, we've got an infinite group of functions that will meet this condition. This gives a sense of what those things look like.